Good morning, everyone. First of all, a reminder of what you may have seen in the quick little update on this new lesson is that I'm going to switch things around based on the calendar, the adjusted calendar, just a little bit. We're going to skip section 5-6 topic and let that be our final topic of the year. And so we are going to move on to the 5.7 topic. And keep in mind where we're at right now is just kind of building the number of functions that we can integrate. This one is going to allow us, or this new topic is going to allow us to integrate the other trig functions. We already know sine and cosine, but what about the rest of them? Again, this will be a two-parter. Mainly, it's going to be about examples. Because remember, it's just practice and making good decisions and recognizing an integral and choosing the right method that is going to be the challenge really from here to the end of the semester. So here's what we have so far. We know that the integral of 1 over x is log x. The reason we know that is because the derivative of log x is 1 over x. Now we do make one little adjustment here, and that is you will see an absolute value symbol around the x. And of course, we have to have the absolute value symbol because if we try to make this a definite integral, the log is only defined for positive numbers. So whatever the x is, it must be a positive value, or at least what's inside the log. So it's not a big issue, but something that we may have to be careful of when we're dealing with definite integrals. So let's just see how this works. There's no real theory here. It's just trying to recognize how we can use this little known fact. So here are some examples. First, up to now, we would try to deal with this type of an expression. We realize we don't have a quotient rule, we don't have a chain rule, we don't have a product rule in integration. What helps us with all of those are several other rules, and mainly our U substitution, which was, again, our latest topic, which was a biggie, and I'm sure you're still working through and maybe even struggling through some of those problems. But even if we don't need to use a U substitution, I like to write it out. So let's see what happens here. It's definitely a quotient. You can even think of it as a composite function where it's 1 over something. So I'm going to let x be the 4x plus 1. Sorry, let u. So if u is 4x plus 1, du is 4 dx. That's our differential. Hopefully you've been doing that a lot lately. And then as we start changing this thing to u values, it becomes 1 over u, of course. But the dx has to be replaced. And if I solve for dx, it's 1/4 du. Well, the du can continue to be outside or inside the integral. The 1/4 can always be thought of as a number outside the integral. We've used that many times. Now I can do the calculus. The integral of 1 over u is log u. And then, as usual, we move it back to x values. We get 1/4 the log of 4x plus 1. These should be absolute value symbols, but I would accept this. Now, if we wanted to check it, as always, we can differentiate. Sometimes it's very convenient to do. Other times it's almost as tough as the integral itself. So sometimes you have to trust yourself. But that's how we can make use of something we really already knew in a little bit different situation along with U substitution. Let's continue to look at some examples. Here we're going to be faced with x over x squared plus 1. And we're going to make this a definite integral from 0 to 3. So this could actually be an application of area. I could maybe ask you to find the area under the curve x over x squared plus 1 from 0 to 3. So you could graph it and get a better feel for what it looks like, but we're really trying to find the area. Or we could be asked to find the area. So let's see what we got here. Similar idea. It's a quotient. So I'm going to let the denominator of the quotient be u, which is a very common method. Not always going to work, but we should try it. du is then 2x dx. You notice I pretty much have the x dx, but not the 2, but I can adjust. So the same old thing, if I change it back to u values, all of this is just u. Now the x dx part, x dx. If I solve for x dx, that's going to be 1/2 du. I could put the du on top of the u, but I'd rather not. And here we go again. We now integrate it. Put it back in terms of x's. Now here we do not have to put absolute value symbols around it, because I don't care what x value I choose. If I square it, it's positive. If I add 1, it's even more positive. So there we go. And again, we can check it. So I've made some decisions here. But one thing I want you to realize is, as far as our rules of integration, we really are very limited. We know the integral of e to the x is e to the x. We know the integral of x to the n is just using the power rule. And we know the integral of 1 over x is log x. So the u substitution is just a way to get us to this point. So many of these are going to look very similar towards the end. Let's continue. Here we have a function involving trig. We want to integrate secant squared over tangent. Secant squared over tangent. I will let you, well, even before I try to think about this, you notice here I let the x squared plus 1 be u because I knew the derivative was close to x. In this case, and I just look at these functions, I know that the derivative of tangent is secant squared. So if the derivative of tangent is secant squared, it would seem reasonable to let u equal tangent. Then du happens to be secant squared dx, which is exactly what I need. So now this function becomes nothing more than the same old thing. 1 over u du, which is the log of u. Changing it back to x values, it's the log of tangent. Of course, plus c. So, last step of every single one of these problems is pretty much the same. Let's move on to something even more advanced. X squared plus x plus 1 over x squared plus 1. Now this is a situation that if you're very creative mathematically, you can get around what I'm going to do next. But when we have a quotient and the numerator is equal or greater in degree than the denominator, long division will help us out. So I'm going to have to use long division. If I use long division, I basically take x squared plus x plus 1. I divide it by x squared plus 1. Sorry, I squeezed that in there. Okay. What do we multiply x squared by to get x squared? 1. So we do it. We then subtract. X minus 0 is x. So that's basically going to be our remainder. So all of this, x squared plus x plus 1 over x squared plus 1 is the same as this. Identical. So all I have to do now is integrate that. 1 plus x over x squared plus 1. So I'm basically integrating two separate functions. We can always separate them. The integral of 1 is just x. Well, look, we just found the integral of x over x squared plus 1 in this problem. So I might as well use it. And there we have it. Now, I did mention that algebraically, if you can see through some stuff, we have another way of possibly simplifying this expression. This may seem a little creative or crazy, but I'm going to do it. I can rearrange this top as x squared plus 1 plus x. And we know that I can put this denominator under each of these two terms. So if you're all-powerful mathematically, you can see this expression as this expression. Because if you would add these two together, you would get that. Of course, that's 1. And then this we have right here. So it's a way to avoid this procedure of long division, but you're really ending up in the same spot. Okay, I know this has been a lot. There's one more example I want to look at, and then with the second part, we'll get into some of the trig functions. This very last one is integrating 1 over x log x. Decision making is so important. As I've said, if you aren't sure what to do, let u be part of the function you're looking at, and then go with it and see where it takes you. Hopefully it won't lead to a dead end. In this case, I really don't want to let u be the whole denominator, because then the derivative would be a product rule. I could let u be x, but here's a hint, never let u be x. It's not going to help one bit, it's just going to change the letters. So maybe it would make sense to let u be log x and just see what happens. So if u would equal log x, the derivative, or du, would be 1 over x times log dx. And it turns out that's exactly what we have. Because if I want to kind of rewrite this, I could write that as 1 over log x times 1 over x. Now if I go ahead and use u substitution, all of this here becomes 1 over u, and then 1 over x dx is the same thing as du. Well, that's just the log of u plus c. But what is u? U is the log of x. Now, I'm not going to argue that that's a rather interesting or unique or scary function, the log of x. But it's absolutely correct in this example. So, we're using something that is very simple on the surface, but as we dig deeper into more and more advanced problems, we have to see how that simple little fact and rule can lead to helping us with a big variety of integrals. Again, I'll be back with part 2, taking a look at the trig functions in just a few minutes.